In this video, we will focus on power and efficiency. Previously, I defined power for you. I told you power is the rate of change of energy or rate of doing work. Let's start with an example. Imagine an ant takes a cup of rice from the ground to a hole in the wall. We have a cup of rice here, and the ant tries to take it to a hole 8 meters above the ground. It takes a week to take all. Okay. If you do the same activity, it takes 7 seconds. Of course, you are more powerful than that. But what do we mean by power? Who has done greater work? The work done against gravity to take this cup of rice to that specific altitude is minimum mgh. At least you have to do this work against gravity because you are saving gravitational potential energy in this rice, in this cup of rice, to take it to that specific height. So it's the minimum work done. No matter if you are doing that or the ant, same. So the work done is the same for both. Who has done the job faster? Of course, you have done it faster. 7 seconds compared to a week. You are much faster. What's the difference between you and the ant? Okay, the difference is exactly power. You have done a specific work like the ant, but the time taken for that is much smaller for you. So if I divide the work done by the time, although the work done is the same for both, but this ratio is different for you and the ant. It's called power. The rate of doing work, the total work done or the energy consumed divided by the total time taken. It's measured in joules per second, which is also called watts. So power, the quantity power is used to measure the rate of doing work. In other words, it is the number of joules that can be converted every second. So let's define it as the work done per the time taken or energy transferred per time taken. It's measured in SI units in joules per second, which is watts. A car of mass 1600 kg is initially at rest and accelerates uniformly at 2.5 meter per second squared. Okay, so acceleration is given. A constant force of 500 Newton opposes the motion of the car. So we have a resistive force of 500 Newton against the motion. Calculate the driving force acting on the car. Let's say the driving force is F. To find that driving force, which is part of the net force, we can use the Newton's second law. F net equals ma. F net is the driving force minus resistive force. F minus 500. It's going to be 1600 mass times 2.5 acceleration. So the driving force is 4500 Newton. Part B, for the first 10 seconds of motion, calculate part I, the total work done by the driving force, and part I, the average power developed by the car. Here again, even I is focused on the driving force developed by the car. Okay, here basically the work done by the driving force is Fx because we suppose that the driving force acted on the car has the same direction as the displacement. So theta is 0 and Fx cosine of 0, cosine is 1, so it's Fx. But there is another problem. What the x is? The displacement. It's an accelerated motion starting from rest. Initial velocity is 0. So x is going to be a half of at squared. We know the acceleration, we know the time, 10 seconds, so we can find the x. So let's substitute x for a half of at squared. Then plug in the values. This is the driving force, this is the acceleration, and it's the time to the power of 2. The answer is going to be 56.2500 joules. The last part, the average power developed by the car. The power is going to be the total work done by the driving force divided by 10 seconds. Time is 10 seconds. And the answer is going to be 56.25 kilowatts. Here, kilo stands for 10 to 3. A cyclist rides up 1.5 kilometer along hill at a constant speed in a time of 350 seconds. So here we can model it with a ramp This is the cyclist, and the total distance traveled along the hill seems to be 1.5 kilometer, and the time taken 350 seconds. Time is 350 seconds. The cyclist maintains a power of 240 watts. Power of the cyclist 240 watts. And the hill makes an angle of 3 degrees with the horizontal. Okay, so the angle is 3 degrees. The mass of the cyclist and the bicycle is 80 kilogram. Mass is also 80 kilogram. Total mass. Calculate the total work done by the cyclist. We have different approaches here, but the easiest one is the relationship between power and the time. Don't bother yourself, it's very easy because we know the power, 240 watts, and also we know the time, 350 seconds. So the answer is very easy, just you should multiply 240 by 350. The answer is 84 kilojoules. Again, kilo here stands for 10 to 3 for abbreviation. Part B, the forward force exerted on the system of the cyclist and the bicycle, the forward force. Let's say this is our cyclist, okay? There is a forward force acting on the system to take the object, the whole system uphill, okay? Here, let's say the work done is force times displacement. We know the work done by the cyclist, okay? We found it already. And also we know the displacement. It's gonna be 1.5 kilometer given in the question. So let's plug in the values and find the force. This is 1.5 kilometer, 10 to 3. Left side 84 kilojoules. Kilo again 10 to 3. Here we use all quantities in SI units. And the answer is gonna be 56 Newton. This is the driving force. Part C, the magnitude of the resistive force acting on the system. Resistive force. Again, let's suppose the cyclist is here. This is the forward force. There are two forces acting on the bicycle. First is mg sine of 3 degrees and the other is the resistive force, friction. What the mg sine of 3 is? You know, in this type of questions which are involved with object on a ramp, we can say if this is the object on the ramp, if this is theta, here we have a downward force of mg, and I draw a dashed line perpendicular to the ramp, the other parallel to the ramp, and it's very easy to prove that this is also theta. So the normal force, the normal component of mg on the ramp is mg cosine of theta, and the other is the parallel force, component of the force along the ramp, which is mg sine of theta. Here we have used it. It's exactly mg sine of 3 degrees. And we are looking for the resistive force. We know that the cyclist goes at a constant velocity, okay? So let's say it's constant velocity. Constant velocity means that the net force is 0. So the forward force will cancel these two and keeps a constant velocity. So let's say it's 56. The driving force is equal to mg sine of 3 degrees. This is the mass, this is the gravitational acceleration, and finally the resistive force. Then we will find the resistive force for 15 Newton. Power in a different version. I told you power is W over T. Let's say this is the work done by the forward force of the car. So it's the power developed by the forward force. Basically, you know that the car is, in real world, is acted by a resistive force of F, so a drag force of F, small f. Anyway, and now let's suppose that the car is moving at constant speed. So there is no acceleration. Acceleration is 0. And let's say at a time t, the car will displace for x meters. So the work done by the forward force is the force times displacement divided by time. As the speed of the car is constant, so x over t is gonna be the v. That's all. This is the power developed by the car, and this is the driving force, and this is the speed of the car, constant speed of the car. Now look at this question. How to maintain constant acceleration? What if the car is not at a constant speed? It's accelerated. What should I do? You know that the forward force minus the resistive force can make the net force for you. So acceleration is F net divided by mass. Capital F minus small f divided by m. This is the acceleration. Now I go back to the formula. The power developed by the forward force is the forward force times the speed. But speed is not constant. You know, the speed is at plus v naught. V naught is the initial speed. Let's say the car starts from rest, okay? If this is so, the power developed by the forward force is the forward force times acceleration times time. Now we have a very challenging part. Even if I keep a constant forward force and a constant acceleration, I have to apply larger and larger power because as the time goes on, I need more power developed by the car. So if you are going to keep a constant acceleration for the car, you have to apply larger and larger power by the car. Anyway, there is something I told you, a general relation for acceleration, force minus resistive force divided by mass. But in dynamics, I mentioned that this resistive force, the drag force, is proportional to v squared. So we have another challenge. To keep the constant acceleration, not only you have to develop the power because of time, but also you have to increase that force because this resistive force is also increasing. So you need more and more and more forward force and power. So the challenge is not just the time is going on. Also, we have another challenge, increasing resistive force. This is why for a limited power for the car, you don't expect infinite velocity. Actually, the velocity cannot be infinite. After a while, you know that in dynamics, this force is going to be equal to the driving force and the car has no acceleration. So instead of using power is equal to F at, as we don't have any acceleration when the car goes to maximum speed, here you will have F times maximum speed. It's the maximum power developed by the car. Okay, this is the forward force developed by the car. This is the maximum power developed by the car, and this is the maximum speed. The reason for the maximum speed is that the driving force has to cancel the drag force, and the drag force is proportional to v squared. So at higher and higher speed, you need larger and larger forward force to keep constant acceleration. So it's very complicated, as you see. Indeed, you know that cars cannot accelerate to infinity. This is because of the limited power the engine can develop. A car is traveling at a constant speed of 25 meters per second and its engine is producing a useful power output of 20 kilowatts. Okay, so calculate the driving force required to maintain this speed. It's very easy because the speed is constant, so I just use Fv. And then I plug in the values. Kilowatt means 10 to 3, 20, 10 to 3, right side 25 meters per second. So the force is going to be 800 Newton. This is the forward force generated by the car. Efficiency. In general, efficiency is defined for a machine. The machine in general has an input total energy in any form. Maybe for the car is in the form of electricity or the fuel, and the useful work out, okay, or the useful energy out. Basically, the efficiency is the ratio of the useful work out divided by total energy in, or the useful power out divided by the total power in. You know that if you divide the energy by time, you will get the power. So it's gonna be the power in, and useful work out divided by time is gonna be the power out. So it's the same. You can use any of these two fractions. Efficiency has no unit because basically upstairs and downstairs have the same unit, joule over joule, or maybe watt over watt, but it must be logically less than 1 because you cannot expect larger useful work out larger than total input energy in. Otherwise, it will have violation of conservation of energy. So efficiency is always less than 1. And if you multiply that fraction by 100, you will get the efficiency in percent. Okay, let's go over this question. An electric motor raises a weight of 150 through a height of 7.2 meters. So we have uh, an electric motor, it will lift up a weight. The energy supplied to the motor during this process is this. So 3.5 to 4 is the total energy in. So the work in or energy in is 3.5 to 4 joules. Calculate the increase in gravitational potential energy. Okay, it's very easy. The minimum force I need to lift up the object must be equal to mg. Okay, at least to keep a constant speed upward. And so this force is mg. And also you know that this vertical displacement is h. So this is gonna be mgh, change in potential energy, of course, gravitational potential energy. So let's do it like that. I will substitute the mass for the weight for, the mg for 150 is given directly here. And 7.2 is the total vertical displacement. It's 1080 joules. The next part, efficiency of the process. Look at this. The total work in is given. Efficiency, I know that, is the work out divided by work in. Okay. The work out is the useful work out done by the machine. Basically, it's exactly the change in gravitational potential energy. It's the useful work out, something that the engine or the motor has done for me. Okay, so here I will substitute that for 1080, and downstairs the total work in is 3.5 to 4 as given in the question. So the answer is 0.31. As you see, it's smaller than 1, and if you multiply it by 100, you can get the answer in percentage, 31%. That's all. Thank you very much. Thank you for being with me, and thank you for your attention. Take care. See you soon.